Welcome to EDU World Space.
So in this problem, we have a rock being thrown from a cliff that's 45 meters high at a velocity of 20 meters per second, while at the bottom we have a person running at 6 meters per second. And what we need to do is we need to find the value of theta so that the runner on the ground can catch the ball. So what we need to do is we need to equate this horizontal component, we're going to call Vx, to the velocity of the runner. So if we use our trig formula, cosine theta is equal to adjacent Vx over the hypotenuse, which is the initial velocity, we can substitute 6 in for Vx. So we have cosine theta is equal to 6 over the initial velocity 20. And after doing the reverse cosine, we find that theta is equal to 72.5 degrees. Now next, we need to find the distance that the runner travels before they catch the ball. And so first we need to use one of our kinematic formulas to find time. So we're going to use delta y is equal to the initial velocity in the y direction times t plus 1/2 acceleration times time squared. So we're looking for time. Acceleration is going to be due to gravity. So it's going to be negative 9.8 meters per second squared. And we can easily find what the initial velocity is in the y direction because now we have the angle. So it's just sine theta, which is 72.5, is equal to v naught y over 20. And we see that that comes out to v naught y is equal to 19.1. So now our delta y, so the ball ends at height 0 and it starts at a height of 45. So delta y is going to be 0 minus 45, which is negative 45. So we can plug everything in. Negative 45 is equal to 19.1 minus 9.8 divided by 2 is 4.9. T squared, sorry, there's a t over here. And now we just solve for t. We can use that by equating it to 0. 45 plus 19.1 t minus 4.9 t squared. We can use a quadratic formula where t is equal to negative 19.1 plus or minus the square root of b squared, 19.1 squared, minus 4a c all over 2a. So doing all the math, we can see that t comes out to negative 1.65 and also 5.55. So in this case, we're obviously going to use the positive value for time because time can't be negative in this situation. So we can easily plug that into our equation for horizontal distance. Velocity equals distance over time. So we have our velocity of 6 is equal to the distance over time. And we find that the distance that the runner runs at the point she catches the ball is equal to 33.3 meters. Now, the last thing we need to do is sketch the trajectory of the ball as viewed by a person at rest on the ground and the runner. So we have the ball. And so if you're a person on the ground, not running, you're going to see the ball do an arc like normal and land on the ground. However, if you are the runner, right, and you're going this way, the ball is also going this way. So from the runner's perspective, all the runner sees is the ball come straight down. So without those green arrows, from the runner's perspective, all they're going to see is the ball drop.